In this recording, I'll work a few more examples. This first one is just a reminder, more of an example. What is the difference between an electrical field and an electrical force? For an electrical field, you need just one charge. An electrical force, you need two charges. And the relationship between them, F, is QE. The force is a result of an electrical field. And whenever you have a charge, it's going to have an electrical field associated with it. Okay, let's work this example here. It is asking us to calculate the electrical field at point A due to these three charges. Okay, we have two of them are positive and one of them is negative. Now remember the electrical field expression. It is E is K Q over R squared. This is in magnitude. So we are going to calculate it for each one of them. And then just a few things before we do that. I'm going to draw the electrical field due to each of the charges. Due to charge, let's call this charge B, C, and D. So the electrical field due to charge D is going to point away from charge D, since charge D is positive. So it's going to be like this. So this is ED. The electrical field due to B, to charge B, is going to point away from charge B, since charge B is positive. So it's going to point like this, EB. Now the electrical field due to charge C, since charge C is negative, is going to point towards charge C. It's going to be like this, EC. And all of them are given by the expression that I wrote above. Now, we'll use that expression to find the magnitude of each one of them. So let's start with EB. So we said it's K, so it's the absolute value, so it's 9 10 to the 9 Newton meter squared per Coulomb squared. And then Q, which is 7 10 to the minus 6 coulombs, over the distance separating B from A, which is 4 meters squared. Okay, I'm going to calculate this in the side. So what we have is 9 to the 9 times 7 to the minus 6 divided by 16. Okay, that gives us 3,938 newtons per coulombs. Okay, let's do the same thing to the easy one first, ED. Okay, same expression. The only difference here, I'm going to have 6 meters for the distance and 2 for the charge. So it's going to be, because of space, I'm not going to write the units here, 9 10 to the 9. And then we have for the charge, it's going to be 2 10 to the minus 6 coulombs. And then for the distance, it's going to be, we said 6 meters squared. Okay, and this should give us 9 10 to the 9 times 2 to the minus 6, so that's 18 to the 3, and then divided by 36. So that gives us 500 Newton coulombs. Okay, and now we need to do EC. So it is 9 10 to the 9 times 3.5 10 to the minus 6 coulombs. And now the distance squared, this is the distance we are looking for. It is the hypotenuse of the triangle made up of 6 meters on one side and 4 meters on one side. So it's going to be 6 meters squared plus 4 meters squared. Which is 606 newtons per coulomb. Okay. Now, these are the individual electrical fields. To add them up, we need to use vectors to be able to add them since they are vectors. Okay. The direction for EC, we need to figure out this angle here. And that angle, since this side is 4 meters and this side 6 meters, the tangent of that angle theta is going to be equal to 4 meters over 6 meters. And that gives me an angle of 33.7 degrees. Okay, now, so I'm going to try to use the space wisely if I can. Now this is EB. ED. AC. And this is the sum. This is the x component and this is the y component. Now, EB does not have an x component, so that's 0. Since it's along the vertical axis, taking this as x and this as y. Now, its y component is the full EB, so it's 3,938 newtons per coulomb. ED has a negative x component, which is the full ED minus 500 Newton per coulomb. Now, its y component is 0. It does not have any component along the y. Now, for EC, it's a different story. We have to worry about both x and y components. So, for the x component, it's going to be 606 newtons per coulombs times cosine of 33.7. Okay, again I repeat it, 606 newtons per coulombs times cosine of 33.7. So that gives me about 504. Now, for the y component, it's going to give us, okay, of course it is 606 newtons per coulomb times sine of 33.7, but it's with a negative sign since it's pointing down. So that's going to be minus 336 newtons per coulombs. Okay, now when I add these, I get 4 newtons per coulombs, and the others, they add up 3,938 minus 336. That gives us 3,600 newtons per coulombs. Okay. Now within significant digits, this is basically 0. I carry too many digits here, but anyway. So these are the components of my electrical field. my magnitude, the magnitude of that electrical field is going to be, we do square root of 3600 newtons per coulombs squared plus 4 newtons per coulomb squared. So that comes out to be 3600 newtons per coulomb. That's the magnitude. And the direction is, you do inverse tangent of 3600 divided by 4, the y over the x, and you do get the angle there, and it gives us a 90-degree angle, which is essentially saying the y component of EC is canceling EB, and the x component no, it's the opposite. The x component is canceling ED, and the y component is just canceling a part of EB. So the overall electrical field is going to be along the vertical axis along EP. Okay, now the next question is asking us, what if we bring a -3 microcoulomb charge to point A? What force would it feel? This is the nice thing. Now, it is a negative charge, which means, remember, F is equal to QE, which means it's going to be opposite in direction to the direction of the electrical field. That means my force is going to point this way when the electrical field is pointed this way. E at A is this way, so the F is going to point that way. Okay? Moreover, so the angle is going to be -90 degrees. And then the magnitude of F, we can find it by just multiplying the charge, 3×10⁻⁶ coulombs, by the 3600, I believe, newtons per coulomb. So it is 10.8 millinewtons, 10⁻⁶, and then, okay, 10.8, 10⁻³ newtons.